me just check. Quick check.
We already have 4 people waiting in the room.
Yeah, that's promising.
Good. I hope everything will get better today.
Yeah, I know. If 94 have registered, so
Yeah, 94.
keeping my fingers crossed.
Usually we would expect 20 to 30 from that Danish, right? And that would be about what we would
Hmm.
expect, yeah. Maybe a little bit, but around that number, yeah.
Yeah, it's 5 now, so.
But that's a good sign. 2 minutes early is healthy, yeah. Right, good luck. Leave you to it. Okay, we can go now.
Thank you.
Let everyone in, Sophie.
Yes. Good luck, my mate, Dennis.
Thank you.
G'day, Phil. We'll be coming over next week.
Sorry, just unmuted myself, I think.
Yeah, that's right. That's why I just asked you to. Yeah, we're coming over next week. We're going down to Andreas and I are coming over
Oh,
to go down to Worsley to talk about the rheology
cool.
stuff. So
Excellent.
we might try and organise a time to catch up with you as well.
That'd be excellent.
Yeah. So thanks for coming along.
No, wouldn't miss it. I told someone I know in Chile about it, but it's not a great time for her.
No. They'd be just, what is it?
Probably about
8 hours in front. So they'd
2
be
a.m.
getting
or
up.
something like that.
Yeah. That's all right. I'll just put you back on mute. They will be starting in about 1 minute. Go for it, Sylvie. I reckon we'll take it off from there. So welcome everybody to today's webinar on preventing high impact thickener failures through bed level measurements. My name is Matt Smith and I'm the technical specialist for the SmartDiver at PLA Process Analyzers. Today's session will be hosted by my colleague Danish, and he looks after the marketing at PLA Process Analyzers. At PLA, Danish works closely with our engineering and commissioning teams, and much of his role is focused on understanding how SmartDiver is actually used on operating sites, what problems it solves, and where it delivers value. So I'll hand it over to Danish.
Thank you, Matt. Thank you, everyone, for joining in. My name is Danish Merchant, and we'll talk about bed level measurements today. So at PLA Process Analyzers, we are based in Melbourne, Australia, and we manufacture rugged process analyzers for the mineral processing industry. And SmartDiver is one of our flagship technologies. So today we will talk about common dewatering challenges, academic research findings on thickener performance, real-world applications of this knowledge with a brief on SmartDiver capabilities and applications, case studies demonstrating operational improvements, and we'll try to cover these topics in about 40 minutes or so that we can have some time for questions as well. And please feel free to ask any questions at any point during the presentation. There is also a chat option in this webinar. So let's start by exploring why a better control of the thickener matters. Effective thickener control prevents critical operational failures such as process stoppages and lost production, product contamination, reduced process efficiency, environmental issues such as water loss or reagent loss, and in general, suboptimal process outcomes. Even though these are very costly mistakes, yet in many plants, the thickener is controlled with limited visibility of what's actually happening inside the tank. From an operational perspective, there are only two levers available to control the thickener: the flocculant rate and the underflow discharge rate. Everything else, the feed rate, solids loading, ore mineralogy, clay content, particle size, is all imposed on the thickener. So without knowing how the thickener is responding internally to these challenges, operators are forced to react late, often by overdosing flocks or backing off throughput. Bed level measurement can address these fundamental gaps. So there has been a considerable amount of research done in the operation of a thickener. Today we will delve into topics related to thickener zones, settling behavior, and correlation between various performance parameters. So the very first research paper that cited these bed levels was back in 1916 by Coe and Clevenger. This still remains as the foundational work for understanding settling behavior. It describes four distinct zones within thickener, these ones, and we'll talk about them quickly. So the topmost is the clarity, which is the uppermost layer of the tank where liquid has largely clarified and yet to be removed as underflow. Interface is a free settling zone where solids begin to settle under gravity. Flocculants help enhance particle aggregation and speed up the settling. The mud or the gel point is a loosely structured bed. There is no solid settling freely, but they begin to compress under their own weight. And heavy mud is the thixotropic bottommost layer of the tank where the solids are almost immobile, and this represents the final stage of the dewatering process. This can also be represented in a continuous flow thickener tank. And the key thing to note is these zones and these layers are not static. They shift continuously depending on feed conditions, flocculant performance, and other operating parameters. This is where measuring bed levels become critical. So Thickener research has pointed out that bed levels have correlation with key performance metrics such as solid flux, which is the rate at which solids settle through the thickener. The underflow density or the concentration is the density of solids discharged from the thickener. Residence time is the time solids spend in the thickener, which affects its dewatering efficiency. And steady state operation is a theoretical stage where the feed rate, underflow concentration, bed levels, they all remain stable over time, and this ensures consistent and predictable performance. So monitoring bed level enables operators to maintain optimal settling zones, and optimum height for each zone for steady state operation is based on the site conditions. So adjusting, the second is adjusting flocculation dose for optimum settling of the zone height for hindered settling, adjusting underflow by maintaining optimum mud height for the desired underflow density, and changes in level can indicate process upsets such as donut flaring or rake bogging. If we scheme out all the popular sensors and how a thickener is optimized by the operator, most thickeners are equipped with just measuring the rake torque and the bed pressure. And bed pressure, for example, cannot measure the density of the inventory accurately because it's based on various assumptions. And rake torque can remain stable at low to mid ranges, but it increases exponentially at higher loads, causing rapid loss of control. A lot of sites can also have overflow turbidity meter, which is again an indicating meter which is lagging in nature, and by the time it registers high solids, the contamination has already occurred. What we are proposing is to improve visibility of the dewatering process within the thickener, adding these two measurements of interface and mud level can help thickener control. So the interface level is the transition between clarity and free settling. This helps to control mostly the flocculant addition. The mud level over here is the transition between free settling and hindered settling, and this variable will help to control the underflow rate. So these two data points, the flocculants and the underflow, are provided to effectively manage the operation levers. So if we go from theory to the real world, bed level measurements isn't entirely a new as a concept. It has been around for a long while, but it's been very difficult to measure reliably in harsh, large overprocessing thickness. In this section, we will cover how SmartDiver navigates this problem, and we'll chart out some case studies from our previous sites as well. So just to give an overview how this mud diver works, we will play a short video as to how it operates. Basically, it's installed on top of the thickener tank, and this is the sensor. It's sitting in the home position on the wash bay assembly, which dives into the tank. So, yep, and some reason, yeah. So basically, the sensor pauses for a few seconds as it dives into the thickener. It takes a reference reading over here, and it descends further into the other zones, and eventually it tips over at this thixotropic zone where the cable
Sorry,
becomes slack.
Danish, just to
Yeah.
interrupt, the video stopped. There it goes. It's back to the original video, but if you want to start it again and see if it never started up.
Yeah, it's having an issue playing, so I thought like I'll just move along.
Sure.
Sorry about that. So yeah, that's when the cable becomes slack, it ascends at the top of the home position where the wash bay sensor activates and gives it a spray so that it's ready for the next dive. If we represent the data from the single dive of a SmartDiver, this is how it can be denoted in relation to the schematics of a thickener. We have just rotated by 90 degrees this data representation. So basically, as the sensor passes along the clarity interface and mud zones, it maps out the changes in suspended solids and it creates a profile for each bed. So one minor increase in solids concentration marks out the interface, and one major increase marks out the mud level. This can also be represented in the form of trend profile since it takes multiple dives during the day, and it can be mapped into a trend profile. So we can monitor how flocculation is affecting the settling rate. You can see that the settling zone between the pink dots represented by interface and the green line over here is the mud level. And then you can see that there is like a steady gap between these two. So this can denote that the flocculants are at their optimum capacity. So with SmartDiver, sites can answer critical operational questions such as why rake torque is rising when mud level looks so low, why is underflow density dropping, has the interface collapsed into the mud bed, and these insights are critical for troubleshooting and optimization. So this is how a typical SmartDiver looks. The system includes a control panel, a sensor drum, the power supply unit, and the wash bay assembly, which ensures that the sensor and the cable is clean after every dive. If we open the enclosure box, this is where all the electronics are housed, such as the PLC, motor, and the transmitter. So the overall build quality is quite robust, and hence maintenance requires mainly housekeeping. And the system uses relative measurement changes in solid concentration rather than absolute values, eliminating calibration requirements. This approach tolerates scale buildup and it extends service intervals. This is like a chart roughly just to show the components and the kind of minimum care it needs on a timely basis to get the system running. So we offer 4 different technologies of sensors, right from ultrasonic to conductivity, light attenuation, and fiber optic, depending on your application. But for almost 98% of all applications, we go with the ultrasonic sensor because it suits most application, mostly because of its higher temperature rating of 106 C. So basically, it measures sound attenuation for suspended solids and acoustic impedance for density or specific gravity. So the basic principle is that more the solid it registers, it denotes a higher decibel rating or a higher grams per liter rating. In the past 25 plus years, we have supplied more than 500 smart divers across the world, and we see some great results out of overprocessing. And the most popular ones were alumina, iron ore, mineral sands, copper, zinc, and gold. Recently, we also had success with uranium and carbon capture as well. So we can incorporate bed level measurements in almost any type of the thickener, albeit its size, like the height or the width of it. The standard SmartDiver comes with a cable which is 24-meter long, which should be sufficient for almost all thickener types. So this is from one side of the SmartDiver, this typically a SCADA setup with SmartDiver data integration, as you can see over here. And from the same site, again, if we drill down more data, then it can be represented in the form of a trend profile where all the levels are marked out and the time period is mentioned, and a more detailed summary of the SmartDiver is mentioned, which can be used for thickener control. So theoretically, we can use the mud level to control the underflow pump. The height of the mud gives us an indication that what is the solid's residence time and whether a gel point has been achieved. Optimum mud levels increase residence time, enhancing compaction and underflow density. Similarly, flock dosage can be adjusted on bed levels. A differential control strategy can be implemented. So it depends on the separation of the mud and the interface layer. Smaller separation would indicate faster settling, and which can indicate to reduce the flocculant, and a larger separation can indicate slower settling, and adding a bit of more flocks can bridge that gap. So this is just an oversimplified version of it, of how optimum these levels are. And if the gap narrows too much, or it widens a lot, it can be optimized with bed level measurements. So most underperforming thickeners are overdosed, causing interface and mud levels to merge. And the standard response for most operators is to increase the flocculant dose, which provides a short-term stability, but it creates long-term problems if it goes unchecked. And just to note that optimum levels are based on flocculant types, chemistry of the ore, clay content, etc. So if we revisit this trend profile, as we saw earlier, there is a clear separation between these pink dots, which is the interface, the green trend, which is the mud, which indicates that the bed levels are steady over a period of time. So let's share some case studies from our previous sites. So this is from a US based site trial, and the flocculant, which is denoted in the yellow profile over here, and the interface in the orange. You can see that the flocculant dose increases, the interface level will subsequently decrease, and vice versa. So the relationship is instantaneous. So as in how the flock dosage would move along, the interface most likely would also be moving along. And when we look at this chart, this is from an Australian nickel plant. It's comparing a 6 month study, which is from a time period of before the installing of the SmartDiver and after the installation. The control strategy in this particular site was to manage the flock dosage, and flocculant consumption decreased substantially. So the purple graph is before the SmartDiver, and the green one is after. So the net savings was about $80,000, or 40% reduction in flock dosage. Similarly, the control requirement in this particular study was to reduce the flock dosage along with improving the underflow density. The result was a net increase of 5% in throughput. So this period is before the SmartDiver. This was the transition period during the installation, and this is after installation. You can see like a much tighter graph over here. So from this case study, what we want to highlight is the control parameter was the site wanted to maintain optimum mud levels to increase solid residence time and increase compaction. And overall, they wanted to increase the underflow density. So again, the purple is before the SmartDiver and the blue is after the SmartDiver. And you can see there is like a visible increase in underflow solids after the SmartDiver trial. This is a pretty interesting trend profile from one of our sites where the operator lost control. And the gray period over here denotes the operator's window to react and prevent the problem. As you can see, most of the bed levels were shot up, and this was the window to react to the changes in the thickener. And by actively monitoring these bed levels, you can spot these warning signs early so that you can avoid expensive process upsets. So in general, what overall what we want to say is there has been decades of academic research that has established the relationship between bed levels and dewatering performance. These levels can shift continuously based on several process variables, making real-time visibility essential for effective control. The challenge has always been measuring bed levels reliably in large, harsh overprocessing environments where high temperatures, scaling, or abrasive slurries cause conventional instruments to fail or drift within weeks. SmartDiver can fill this knowledge gap by providing real-time measurements of what's actually happening inside the thickener and access to the data that operators never had before. This visibility enables a fundamental shift in strategy. Operators can now manage operational levers based on real-time data from inside the thickener rather than reacting to downstream symptoms like poor clarity or underflow density. The result can be optimum process outcomes and early detection of process upsets before they hamper the production. And that's it from us today. And if you guys will have any questions, please let us know. We'll be happy to answer them.